Okay, so thanks to have me here today. So yeah, I'm Corentin. I'm working with Katrina Jackman in the Magnetospheric group of Dublin of DIAS Institute since last November. So yes, today I will talk about the magnetospheric radio emission, and I will focus on the Jovian auroral radio emission, so coming from Jupiter, and so I will give you some information on this radio emission, and on the second time of this presentation, I will give you a presentation of the Express code, which allow us to simulate so the name is Exoplanetary and Planetary Radio Emission Simulator, and this code allows us to simulate some of the auroral planetary radio emission that we observe. I will show you how you can use, if you want, this code, which is accessible online and open source. And I will give you some example of applications with Express that allow us to discover some emission, reproduce some other one, and also reproduce some occultation of this radio emission seen by some spacecraft. And if I have some time at the end, I will briefly mention some radio emission produced by other planets or even satellites like Ganymede, for example. I know Katrina give you some information on that this morning. So let's begin with something that you probably already seen this morning with Katrina. So this is the magnetosphere of our solar system. So Mercury, the Earth. So sorry, it's in French because I take that from a French presentation in French, but Earth, Saturn, Jupiter and Ganymede, and Uranus, Neptune, and probably exomagnetosphere. We are still trying to catch that. So you can see that on each of these planetary magnetosphere, you can see here for the Earth. Can you see my pointer, by the way?
Yeah.
I guess so, but okay, cool. So here you can see on top of Earth, you can see some emission in visible. The same for the southern pole of Saturn, but in UV. For Jupiter here and Ganymede also. And for Uranus and Neptune, it's really hard to see, but it's a dot here, a blue dot on the blue surface. And for Neptune, it's even complicated, much more complicated to see this UV or visible optical aurora, I should say. So here, now zoom in on all these planets. So here you have the Earth with the visible aurora on top of the pole, on the northern pole and southern pole, aligned with the magnetic field direction. Here on Jupiter, you have, so here it's on UV wavelength. So you have some UV emission at the southern pole of Jupiter, southern pole of Saturn. You can see here line or circle of brighter emission here on Uranus. This is the UV emission and auroral emission of Uranus. And you also have here auroral emission in the infrared wavelength. So here the same southern pole of Jupiter, but in UV here and in infrared here. And also the same for Saturn. So I will give you some more detail on this emission just after. But before doing that, we can see also, so we have visible emission, UV emission, infrared, and we also have some radio emission, not directly on top of the atmosphere, but at higher altitude above the atmosphere along the magnetic field lines. And you can see here the spectrum. So you have the frequency in the x-axis, and on the y-axis you have the density, the flux density, so the intensity of this emission. You can see that we have here a gray box. This is the part of the emission that we can't see from the ground, because you have on Earth, you have this ionosphere that Laura told you this morning, I guess. So this ionosphere is hiding the emission below 10 megahertz. So you can't see any emission that are emitted in the sky, that are emitted in the direction of the Earth. If these emissions are emitted below 10 megahertz, it's not visible from the Earth. So the only emission, radio emission from the planetary auroral radio emission that we can see from the ground are the emission of IO called the decametric emissions, because it's on the decametric range corresponding to a frequency above 3 or 10 megahertz. So this is the only radio emission that we can see from the ground. And fun fact is that these emissions were discovered in during the 1950s by Burke and Franklin, but it was not, they were not looking for this emission. They were testing their antenna on the Crab pulsar signal, and after processing their signal, they saw that there were something else, another signal, which was compatible with emission produced by Jupiter itself. And then begins the era of the radio emission, the planetary radio emission research. So since we are able to see only the decametric of Jovian decametric emission from the ground, we have to go in space to see the other radio emission of all other planets, including Earth. So on the right, you have some observation made by different spacecraft, WIN for the Earth and Voyager, for example, for the other planets. So Voyager 1 and 2 were the two first spacecraft that flew by the other planets, Jupiter, Saturn, Uranus, and Neptune. And they observed actually emissions, radio emissions, for all the planets of the outer solar system. And we were able to produce this, people were able to produce this kind of plots that give you the intensity, the mean intensity of this emission. So in the rest of the presentation, I will focus mostly on Jupiter. Why I want to focus on Jupiter? First, this is the planets on which I'm working since the beginning of my career as a PhD student. So yeah, it's the planet I'm the most interested in. But also because these planets have the most intense, the most important magnetic field of all the planets of our solar system. So, for example, the magnetic field is something like 4 to 20 Gauss, depending on if you are measuring at the equator of the pole. And for comparison, the Earth's magnetic field is only 0.2 at the equator and 0.6 at the pole. So you can see the huge difference between these two magnetic fields. Also, we have Io, the Galilean moon Io, which has a really intense volcanism that produces something like 1 ton per second of plasma due to the volcanism. So it's a huge source of plasma, and this gives us, it's like an astrophysical laboratory of plasma. So when we have some remote observation with the radio observation or in situ observation with, for example, Galileo spacecraft or Juno, at the time we speak, Juno is orbiting Jupiter. So we have a lot of information of the interaction between the magnetosphere and Jupiter itself by looking at the plasma. Jupiter is a rapid rotator. That's an interesting point. I know that Katrina already told you that this morning. And also we have an intense auroral activity at the contrary of Earth, which is not permanent. At Jupiter, we have almost all the time some UV emission and radio emissions in terms of aurora. So I will focus on that. And which is interesting in terms of radio emission themselves is that since the magnetic field has a huge intensity, and since the emissions are some way linked to this magnetic field amplitude, we have emission from a few kilohertz up to 40 megahertz. Then in the case of the Earth or Saturn, we only have radio emission at a kilometric wavelength, so corresponding to a few hundred of kilohertz. Here we have emission from a few, I should say, hertz up to 40 megahertz. So plenty of different radio emissions.
A related question.
Yeah, sure.
And it's related to that range, but the previous slide where you show all planetary radio emissions, yeah, there's a rapid drop of the Jovian emission at, what is it, in the high frequency end at something like 30 megahertz, is it? Those S bursts there on over, yeah. Is that because the magnetic field is only so strong, so you only see such frequencies?
Yeah, exactly. These emissions here at the drop here are emitted at something like 40 megahertz. So it's a IO decametric emission, and it corresponds to because these emissions are directly linked to the amplitude of the magnetic field. So this limit here is due to the limit of the maximum amplitude of the field of Jupiter. Yeah.
Okay. All right. Thanks.
Yeah, so let's moving on. So I go back briefly on the UV emission because it gives us, it's more easy to see with our eyes, because yeah, we can see here it's the North Pole, and we can see a lot of different emission here. So first, this circle, deformed circle here is called the main oval. So it's emission that are quasi-permanent at Jupiter, and all these UV emissions are produced by electrons that are accelerated along the magnetic field lines, and that these electrons collide with the upper atmosphere, the neutral atmosphere of Jupiter, and so the molecule of this atmosphere begin to be excited, and they have to give back the energy. They are unstable, they can't stay unstable, and they to go back to stable phase, they have to emit the energy they had. So they emit that as a UV emission in this case. So at Earth it's visible. So we also have this main oval, we also have few dots. So here with a tail, this is emission induced by the interaction between Io and Jupiter itself. The same for Europa and Ganymede. And on the center, so polarward of this emission, we have some polar emission, but in this case, we do not know exactly how these emissions are produced. There is a lot of different theories. Actually, we were discussing that during this week at the Magnetospheric of Outer Planet Conference, which is this week. There is a lot of different theory, but not one is fixed actually. But okay, so, and on this magnetic field line that are connected to the main oval, the Io, Europa, and Ganymede footprints. So on top of that, you have some emissions. The radio emissions are produced not on top of the atmosphere of Jupiter, like the UV emission, but far away at a higher altitude above the atmosphere. So this is what we call a dynamic spectra. So dynamic spectra is the way how you can look at the auroral radio emission. So it's time in x-axis and its frequency in y-axis. So here we're looking at a few tens of kilohertz up to 16 megahertz, because it was the limit of the limits on the frequency range of observation of Cassini. And Cassini flew by Jupiter end of 2000. And on this plot, you can see a lot of different emissions, as in UV. Actually, you have a lot of different emission in UV, and you have also a lot of emission in radio. So you have, for example, this kind of broadband kilometric emission. You have the hectometric emission and the decametric emission. And inside this decametric emission, parts of this decametric emission are controlled by the interaction between Io and Jupiter. And you also have something that is called narrowband emission at the same frequency as broadband, but this is not the same mechanism to produce this emission. I will come back on that in a few slides. So let's have some really science parts. So here it's how we can explain both the main oval emission in UV and also in radio, the sources of decametric, kilometric emission connected to this magnetic field line that are producing the UV emissions, and also after how we can explain this emission of Io. So in the case of the main oval, you have to know that, I already told that, but the volcanism of Io is producing a lot of plasma. It's ejecting a lot of plasma in the magnetosphere of Jupiter, something like a ton per second. So because Jupiter is a fast rotator, so it rotates in 10 hours, while Io the revolution of Io is 42 hours. So it's the plasma emitted by Io is taken by the rotation of Jupiter. So it creates a torus at the orbit of Io. So you have Io, and all along the trajectory of Io, you have the plasma that are produced, that are emitted by Io. Then, because Jupiter is a fast rotator, this plasma is transporting outward by the centrifugal force, and then it creates a plasma sheet. You can see here, it creates a plasma sheet at the equator, the centrifugal equator. This, because you have this plasma that is trying to stay in co-rotation, so to rotate with Jupiter, this creates a radial electric current, E, that I have written here. And this, because of this current and the magnetic field, this gives birth of a current, a J, aligned with the magnetic field. This current closed inside the ionosphere on one point, and it's connected to the plasma sheet on the other point. So since at high latitude, the density is decreasing because most of the plasma is at the centrifugal equator, since the plasma is decreasing when you are going at high latitude, then in order to ensure the continuity of this J current, the electrons have to be accelerated. And by the fact that they are accelerated, some of the these electrons really have a really intense acceleration, and then can go directly through the atmosphere and collide with the atmosphere of Jupiter and produce this UV emission that you are seeing here. For Io, it's a bit different. But it's actually the same mechanism, but it's directly inside Io. Because Io is rotating slower than Jupiter, this creates actually the displacement of Io in the Jovian magnetic field. So it's the Jovian magnetic field that are going faster than Io. It creates a current V, you can see here. And then because of this current and the magnetic field, you have a current E that is producing by the plasma that are ejecting outward. And this gives birth and rise to a current, a G current, same process than in the case of the main oval, but just on the magnetic field lines that are connected with Io. And this current is believed to be carried by something that we are called Alfvén waves. So it's at the Alfvén speed, and the Alfvén speed is dependent on the plasma density. So it's going slower when this perturbation is going slower when it's inside the Io torus, and then really fast when it's here. And due to this current, sometimes the Alfvén ring can expand up to the ionosphere and atmosphere of Jupiter, and it creates this kind of emission induced by Io in UV. So let's go back to the radio emissions. So actually, this kind of currents and mechanism also do not apply only to the UV emission, but because you have accelerated electron all along the magnetic field line connected to Io, for example, or connected to the other magnetic field lines in the case of the main oval, this acceleration of electron can also be able, if instabilities are present, able to produce this radio emission. So let's look at the macroscopic properties of all those emissions that we are seeing here. So first one, the broadband kilometric, ectometric and decametric radiation, they all look as vertex early or vertex late shape. You can see these stripes here. The same for broadband kilometric, ectometric, and decametric, different from the narrowband emission, for example. So this emission extends from a few kilohertz up to 40 megahertz, which is not displayed here, but it's go up to 40 megahertz. These emissions are emitted on a mode that it is called extraordinary mode. This, what is interesting in this extraordinary mode is that the emission become polarized. So it's right-handed on the north, left-handed on the south, but so it gives you an information. If you are able to look at the polarization, you know that if emissions are right-handed, these emissions are coming from the northern hemisphere. And if it's left-handed, it's coming from the southern hemisphere. So it can give you information on the localization of these sources. So we can see some arc shape here. This is due to the fact that these emissions, broadband kilometric, ectometric, and decametric emission, are not emitted in an isotropic way. They are really beamed, they are anisotropic, and these emissions are emitted along what we call an holocone. So it means that the emissions are emitted only on the sheet of this cone. This cone has an opening of something like 75 up to 90 degrees with respect to the magnetic field line where the sources are, and this sheet where the emission is beamed is only a few degrees, maybe 1 degree or 2 degrees. The mechanism that produced this emission is known. It is called the cyclotron mass instability. I will come back on that on a few slides, because it will be really important to really clearly understand this mechanism to be able to reproduce with express code this emission. Let's go to the other kilometric emission called the narrowband kilometric emission. So you have an example here, but you have more example here. So you have narrowband kilometric emission and some emission that we call narrowband low frequency emission that really look like the narrowband kilometric emission, but at lower frequency. So these emissions are emitted between a few kilohertz up to a few hundreds of kilohertz, and they look like some fuzzy patches elongated in time in our dynamic spectrum. We know that from Voyager era, we know that these emissions are emitted probably inside the Io torus at a frequency related to density of the plasma torus. But the emission mechanism is not known with certainty, but different process that I will skip here because it will be in too much detail to explain that. But the only mechanism that we can think of for these emissions are an emission close to the plasma frequency, meaning that it is directly linked, as I said, to the density of the plasma torus. And then finally, you have this kind of emission that we can see all along the observation here, that is called quasi-periodic burst radio emission. So why quasi-periodics? Because the first people that studied this emission seen a quasi-period of this burst repeating every 15 minutes or 40 minutes, which was called quasi-periodic because they are a different period, and it was not exactly 15 and not exactly 14. It was moving a bit around this 15 or 40 time period. And here also, the mechanism is not known with certainty, but we think that it probably emitted we know that it is emitted above the pole because, for example, with Juno, we are flying through the pole and we are seeing a lot more QP emissions than when we are on the equator. But so we know that it's high latitude and high altitude region, the sources, so here. But we do not know exactly the mechanism that are producing this emission. So as you can see, we have plenty of different radio emission, but we still not understand perfectly all these component and the mechanism that are producing this emission. So in the next few slides, we will focus on the decametric emission because it's visible from Earth. And because it was really nicely studied since the 1950s, and we will try to reproduce this emission. So here, for example, you have observation of this decametric emission with Juno. So Juno is a mission, a NASA mission that arrived at Jupiter a few years ago, 2016, on July 2016, and that will be visiting Jupiter up to 2025. So a lot of orbits are to come. And this Juno mission have a lot of different instruments, but the one on which we are interested in to look at this radio data is the plasma wave instrument. So it's two antennas, can see here, and these antennas are listening to these electromagnetic waves, and we are able to then plot this kind of data in a dynamic spectrum, so time here and frequency. Since these decametric radio emission are observable from the ground, it's really interesting to look at this radio emission by using some ground radio observatories, such as the LOFAR one. And here, for example, the Irish part of the LOFAR observation that is located in Beer in Ireland. So you can see here an observation of an IO decametric emissions that last a few hours using the I-LOFAR observation, I-LOFAR stations, which is really interesting with the I-LOFAR station, or in general, the ground-based radio observatory, is that we can have not only one or two antenna as in the spacecraft, but we can have plenty of antenna. And this gives us the opportunity to have high resolution observation of this signal. And you can see that if we are looking just with this kind of resolution, we see one main arc and a few secondary arc here. But when we zoom inside here, so here it's only 1 minute. So here it was 1 hour and a half. Here it's 10 minutes. And here it's only 10 seconds. And you can see that even if we think that we have only one main arc, this arc is composed of a lot of substructures that we call millisecond bursts, because they last only 1 millisecond and then they drift in time and frequency. And this kind of millisecond burst can give us a lot of information on the electrons that are producing this kind of emission, on the localization of the sources in the magnetic field line and in the magnetosphere of Jupiter, etc., etc. So this is things that we are studying at the time we speak. Because yeah, we can see that this is obtained in June this year. So yeah, the next question, and this will be the main part of my talk and the next few slides. The main question is, can we simulate this emission, this decametric emission that we observe since the 50s? So yeah, I already spoiled you. Yes, we can. So just before going to the simulation, only one equation here about this cyclotron mass instability. This is the mechanism that produced these emissions. It has been measured in situ at Earth. This cyclotron mass instability, so CMI theory, was built with the observation at AKR, so auroral kilometric radio emission at Earth, using some different spacecraft that we had on top of this emission. It has been also studied at Saturn with remote observation from space and then in situ observation with Cassini, and on Jupiter since the 50s with space and ground observation near the equator. And since the Juno era, we are observing the sources in situ since we are flying through directly these sources. So the question is it this mechanism universal? Could it be applied also to the exoplanetary? This is an ongoing study also from some colleagues that are looking for this radio emission coming from exoplanets. Really hot topic. So this is the equation of the cyclotron mass instability. So I won't go into much detail in that, but what we have to retain is that these emissions are emitted really close to this cyclotron electronic frequency, which is directly related to the magnetic field amplitude of the planet. And to be able to produce, to trigger these emissions, what we need is what we call a high magnetized depleted plasma, meaning that the magnetic field has to be stronger than the plasma density, much, much stronger. And of course, we need some accelerated electron. I already show you how the currents at Jupiter accelerated these electrons that are then able to produce and to trigger this mechanism, the CMI. So then now go directly onto the code, the express code. So exoplanetary radio emission simulator. So this code, actually it's really easy in terms of physical assumption. So we have the CMI equations that we run in this simulator, and then we just go on straight line wave propagation. So once the wave is emitted, it's going straight line propagation. So what the code, what do we have to feed with the code? We have to give him, so of course, a planet with a magnetic field model. We have to give him the energy of the electrons that are responsible for the emission that we want to look at, to simulate. We need to give him a frequency range, and we need to give him the position of the observer to be able to see what the observer could see or not. And then we built this kind of dynamic spectra, so it's still time here and frequency here, and this is the kind of emission that we are able to produce with the code. And we can directly compare this with the actual observed emission. Yeah, just briefly to mention that A, B, C, D, it's just labeling of our emission that we're observing. A and B meaning northern hemisphere emission, C, D, southern one. A and C are east direction of the observer, and B and D on the west, west part of the field of view of the observer. Okay, so just briefly to mention also what we are observing and why we are simulating emission in the shape of an arc. This is due to the fact that the sources of the emission are linked to magnetic field lines that are rotating with Jupiter. And since these emissions are not isotropic, but strongly anisotropic, only emitted on the sheet of this hollow cone, when the magnetic field line is rotating where the sources are, where the emissions are, when these sources are rotating with Jupiter, the observer only observes, so this kind of arc here is only observing the emission twice or three with the two here, when the beaming, when the cone is entering in the field of view of the observer, and when it's exiting the field of view of the observer. So yeah, so our code Express is accessible online, so it's open source code accessible at this address. You have all of the explanation how to use the code, and you can also download the archive and run the, if you have IDL, so it's an IDL, you have to have IDL, but if you don't have IDL, you can also go directly to this address where you can run the simulation with Express. So for example, if you want to have some pre-configured file to run the simulation, you can go to this address and take one of these many pre-configured files and the results file also that we produced for the Voyager era, for the Cassini era, for Juno era, and for the Earth observer from 1970 to 2025, etc. So you can take a pre-configured file and go to this address. No account is needed to run the simulation. So you go to job list, you select Express, you go to create a new job, then you give the JSON file, so the pre-configured file that will run the simulation where all the parameters are, and then you just click to submit. So it will execute the job simulation. And if it's a simulation, for example, for an IO-induced decametric emission, in 30 seconds or 1 minute, you will have your simulation for 1 day of observation. And then when it's complete, you can download the results in a CDF format that is, it's readable with Python, for example, or Autoplot if you want to have a nice display of this. Express is also used to predict, so predict, not to directly compare, but also to predict, sorry, I will go back, yeah. It's also used to predict the emission that we can see. So for example, to catch emission with I-LOFAR, we use this kind of tool. So for example, on this address, you can select an observer. So for example, here, I-LOFAR. Then you can select, so you have the coordinates, you can select the date. So we can see what we should be able to see next weekend. So actually tonight. So okay, we select start time and end time. We can select the different satellites. So here we want to look at what is induced by IO. And we have some occurrence map that give us some intel on the probability that we will observe the emission. And you can say if you want to have Jupiter visibility. So yes, let's go to submit. And so on the left, bottom left, you have probability map that give you the position and the difference here, of course, different emission of IO. You have the position of Jupiter at the time given here, and you can move Jupiter on it to see when we can observe things. And on the right, you have the simulation. The white part is the time where Jupiter is observable in the sky. And you can see that on the Friday night or Thursday night, you should be able to observe some IO-induced emission. So, okay, for the last few minutes that we have, actually maybe 15 minutes, let's look at the Express application and how, so we can use, as I just showed you, we can use Express to look at, to predict what kind of emission we should be able to see, but we can also take some observation and try to reproduce what we are observing. So we done that a few years ago in 2017. We do that trying to reproduce the observation made by Juno during his first perigee, so his first orbit around Jupiter. So on the bottom, you have some Juno waves observation, and on the top, you have some express simulation. So here we played with the different parameters, so energy of the electrons, position of the sources on the magnetic field connected to IO, and we were able to reproduce with a nice fit the emission that we observed. You can see that we are in terms of frequency or in time, we reproduce well this emission. And we also have an information of the opening of this beaming angle. Since the emission are really strongly anisotropic, we can have information on the opening of the angle, and this gives us some new constraint on the mechanism of this emission. So for sure, here we only looked at 24 hours, I guess, 24 hours of observation, but we can also do that on a long term. So for example, here you have observation of Juno waves for 11 days. And this time, we decide to not trying to fit each arc individually, but to using the previous plot, we took the best parameters set that allow us to reproduce this emission, and we ran a simulation all over these 11 days. And you can see that we are clear, the emission that we are simulated reproduce quite well the emission that we are observing. And we can also, so we can infer that these emissions are produced by the interaction between Io and Jupiter. We have the information on the beaming angle. And what is really interesting also is that only the southern hemisphere emissions reproduced what we are observing here. If I display the northern one, you can see that it's in terms of time, it's okay, but in terms of shape and frequency shape, it's not okay at all. And this gives us information that the emissions that we are observing here are only produced in the southern hemisphere. Another application of Express was to, so we know that in UV, we have emissions produced by the interaction between Io Jupiter, Europa Jupiter, and Ganymede Jupiter. But up to 2017, there were only hints of the presence of Ganymede and Europa decametrics or radio emission. We knew from a few years that since mid 20th century that Io is inducing decametric emission, but there were only hints for Ganymede and Europa. So what we decided to do was to produce a long-term database of simulation of Europa and Ganymede induced decametric emission, and compare this database of simulation to the observation of Cassini during the flyby of Jupiter and during the flyby of Jupiter by Voyager, also the two spacecraft, Voyager 1, Voyager 2. So we compare directly the simulation to the data for, it was representing something like maybe 2 years of data, 6 months for Voyager 1, 6 months for Voyager 2, and 1 year for Cassini. And we compare daily dynamic spectra. So for example, we add, like for example here, a Cassini observation for a given date. So we can see the lot of different structures here, a lot of different arcs, really complicated to determine the origin of that, just like that. Hopefully we have some polarization information. As I said at the beginning of the talk, the northern hemisphere emission are right-handed, so in white here. The southern one are left-handed. So what we can see in this polarization plot is that we can clearly see two main and strong intense arcs that are left-handed, so coming from the southern hemisphere. The other emissions seems to be less structured. So since we already we already know some information on that, we can, if you know already that, you can infer or have some hints that this is induced by some interaction between Moon and Jupiter, but you don't have strong proof of that. But if we compare directly with the simulation made by Express, we can determine that this arc corresponds to the simulation of an IOG arc. And for this one, we can clearly see that we are reproducing well the shape of these emissions by simulating an emission related to Ganymede and a G arc, so an arc coming from the southern hemisphere and the east of the observer. So we done that for Ganymede and Europa, and we were able to detect 100 arc for Ganymede and 100 arc also for Europa. So you can see here, we reproduce properly the IOD emissions and also the Europa C emission that you can see here. So up to this point, Express can be, I proved you that Express can be used as, can be used to predict things, to reproduce things, but also to detect new radio features inside the observation of Jupiter in radio. Recently, we wanted to play with Express a bit more to see if, because here we only only show you some example of reproduction of emission induced by the Galilean moons of Io, Europa, Ganymede. But could we be able also to reproduce all the other decametric emission, for example, that you can see here, all the arc shapes that you see are not related to Galilean moon induced emission, but with decametric emissions, so produced directly by Jupiter itself. So could we be able to reproduce that? So what was interesting during the Galileo era, so Galileo was orbiting Jupiter for a few years, so he flew by during a lot of orbits directly near the moon of Jupiter, so behind Io, Europa, Ganymede, or Callisto. And so here on the top right panel, you have the observer's field of view when Galileo is going behind a moon. For example, it could be Callisto here. And during this time, the sources of the decametric emission is occulted. And on the plot on the left top side, you can see that we are observing decametric emission all the time, except during a few minutes here, corresponding to the time where we are behind Callisto. So the idea was, is it possible to reproduce that with our code, with Express? So here, I will show you a quick movie with Jupiter in the center, and the dots here corresponds to sources that we are simulated with Io. So each point that you are seeing is an emission, actually. So if the A source is here, B, C, and D. So the movie I will show you is a reproduction of the flyby of Galileo, of the flyby of Callisto, sorry, by Galileo. And you will see that at one point, the sources are all occulted at this point. And then it's deocculted, it's appear again. And you can see the first part of the source and at the end, all of the source. So if we take this movie and do a dynamic spectra of this movie, this is what we obtain. And you can see that, so the different color from white to dark gray, it's A, B, C, and D emissions. And you can see that we are really well reproducing the occultation. And even in the ending part of the occultation, you can see that all the sources are deocculted almost at the same time, but the C emission is the last one to reappear from the occultation, corresponding to the time where we are seeing the full intensity again. So that's cool, that's nice. It's funny to see that we are able to quite well reproduce this occultation, but what is the interest behind that? What can we do with this kind of occultation reproduction? Well, actually, it can give you some information on the ionosphere, because the body of the moon is occulting the source, okay, but also the ionosphere above the moon, depending on the frequency, will occult some of the sources, not other one, or it will refract some of the emission. So by looking at when the emissions are occulted and depending on the frequency, this could give you some information on the ionosphere. And we done that because it was part of the preparation plan to the JUICE mission. So I think Katrina already told you about this mission. It will be a mission launched on 2022, arrival at Jupiter in 2030. It will be orbiting Jupiter and will fly over and at the end orbiting Ganymede directly for a few orbits. So we have two instruments that are interesting by this kind of simulation of the reproduction of the occultation, the radio and plasma waves. So it could measure, so by measuring the refraction or the occultation of the source, you will measure the ionosphere, the information about the ionosphere. And also the RIME instrument, it's a radar that will be, with using radar technique, it will sound the moon itself by and one of on the main point is looked at an ocean behind the inside the moon and to have some constraint on the depth of this ocean. The problem is that this radar is working at 9 megahertz, and at 9 megahertz it's quite it's in this region almost. And you can see that you are seeing emission all of the time. So it's radio emission coming from Jupiter, but you are seeing radio emission all the time. So RIME could work only during this part when we are occulted. If they try to work during the time when we are seeing some radio emission at 9 megahertz, it will be more complicated to have a good results of the sounding using this radar. So yeah, that's one of the applications that we can have also with Express. So really briefly, in the 2 minutes that I have left, I will show you other planetary radio emission in 3 slides, because you can see that speaking of only the radio emission of Jupiter took me something like half an hour. So if you have 2 more hours, I can speak more about the Saturn radio emission, Uranus, Neptune, etc. So I will just give you a brief summary of that. So for example, here you have some radio emission and aurora from Saturn. So I think you already saw some dynamic spectra from the Saturn kilometric radio emission this morning. So at Saturn, we have aurora in infrared, in visible, in UV, and in radio emission. But since the magnetic field is not as high as the Jupiter ones, we only have radio emission up to a few hundred of kilohertz, not up to a few megahertz. So you have, of course, this kind of kilometric radio emission that are produced in this with the same mechanism. So the cyclone Mason instability, so the same mechanism than for the broadband kilometric, decametric, and ectometric emission at Jupiter. And you also have, can see here, some fuzzy elongated patches corresponding to the narrow band kilometric emission, similar to the one observed at Jupiter, probably emitted with the same mechanism also, so linked to the plasma density of the magnetosphere. So at Saturn, you also have a moon called Enceladus that has an exosphere and sometimes have some ejection of matter with plume ejection. So the interaction is in a way, it's almost the same than the Europa-Jupiter interaction. So why don't we see all of because we are seeing some Europa UV emission induced by Europa in the atmosphere of Jupiter, and so people were looking at the same for Enceladus. And it took a long time because this emission seems to be weak and really sporadic, but it has been discovered in 2011 by Prior et al. And you can see here, can clearly see in 2 different images taken at 2 different times, footprint, really clearly footprint here, corresponding, matching to the magnetic field line connected to Enceladus. In the radio side, we looked to some radio emission induced by Enceladus, but so far we did not discover them. So maybe with more data, because we have the Cassini data, the mission is over, but since it's really a sporadic emission, probably, maybe we just didn't look the right way. Maybe Express is not enough to look at that. Maybe we have to find other way to look at that. So stay tuned, maybe we'll have some more information in the coming few years. I don't know. And yeah, to finish this presentation, let's talk a few seconds about Ganymede, because Ganymede is the only moon in our solar system that has its own mini magnetosphere. Planets have some magnetosphere, but only Ganymede, it's the only moon which has its own magnetosphere. So it's connected to, it's embedded in the magnetosphere of Jupiter. And because of the configuration of the Jovian magnetosphere and the Ganymede magnetosphere, there is always reconnection between the magnetic field line of Jupiter and the magnetic field line of Ganymede. Some of these magnetic field lines are closed, some are open. And at the frontier between the open and the closed magnetic field line, we can clearly see, on the left here, we can clearly see UV emission produced by the interaction between the electron of the Jovian magnetosphere and the atmosphere of Ganymede. And we also have some radio emission, so not the same, it's not cyclotron maser instability emission, it's other kind of emission, but we have also emission that are directly produced by interaction inside the magnetosphere of Ganymede. So it's not the same emission than the decametric induced by Ganymede. Here it's really emission produced by interaction inside the magnetosphere of Ganymede. And that's the end of my presentation. I can't resist to show you some nice picture. So it's not radio emissions at all, but it's emission. It's observation and images that were taken by Juno the next few years or even months, because we have some infrared imagers and also visible imager. So on top, you have some infrared emission of Jupiter taken by Juno. On the middle, you have also infrared emissions, but not of the aurorae, but of the cyclones of Jupiter. And you can see that it looks like there are some impressive cyclones, and these cyclones are not permanent, but we are flying by the pole every 53 days, and every 53 days we are seeing these huge cyclones at the pole of Jupiter. Here you have view of the half of Jupiter, and on the right, this is a really nice picture taken 7th of June, so this 1 month ago, because Juno flew very close to Ganymede and was able to take an impressive and awesome picture of Ganymede. So that's conclude my presentation. Thanks for listening, and I will take your question if you have.
Great, thank you so much, Corentin. That was so interesting. And these images are amazing. It's mad how much Ganymede actually just looks like the moon.
Yeah. Actually, there is a picture that where you have it's a Photoshop, of course, but you have half the moon and half Ganymede, and it looks like really similar. But it looks like also on Ganymede you have much more strips that we don't have. So you have the crater like on the moon, but on the moon you don't have these kind of strips like fractures in the surface, probably due to ancient tectonic movement, or I don't know exactly, but yeah.
Cool. That's fantastic. Pijing, do you have a question?
Oh, yes. Thank you. Very nice talk. Very interesting. Actually, I have a few questions. One of them is, I noticed the color map of the simulation is degree. It's what's the meaning of degree?
Actually, so I have to show you two different plots. So yeah, on this one, for example, yeah, it's degree, and this corresponds to the opening of the beaming angle. So let me go to another plot, this one. So you can see that, as I was telling during the presentation, the emission is not isotropic, it's anisotropic, and it's beamed along a cone and only on the sheet of the cone. So the value on degree inside our simulation are the opening of the angle. So the angle between the magnetic field line and the part of the cone that is emitting the wave.
Okay, so it's theta, right?
Yeah, it's a theta, the theta, yeah.
Oh, but I noticed this is relevant to the intensity below in the below panel comparison to the simulation. observation. Yeah.
Yeah, actually, the z axis is not comparable between both. Here it's just it's intensity of the waves. Here it's opening of the beaming angle. There is no direct link between the intensity and the beaming angle, but there is one small thing that you can compare is that there were some theoretical and simulating work on that. And because this, the CMI, so cyclotron mass instability, is a mechanism that amplifies a wave. And it has been shown that if the beaming angle is too low, so close to 60 degrees probably, or 75. So here in the color, the mechanism is not powerful enough to amplify the wave that we can see. Oh. And that's why that was one of the results of this paper, is that we can clearly see on both sides, and actually also here, that when the beaming angle is below this 70 plus or minus 4 degree, we can't observe any emission, and the mechanism is not powerful enough, or can't amplify the wave.
And I think it is possible to calculate the growth rate of CMI and to estimate the intensity in some sort of extension.
Yeah, it's possible, but actually, the express code is only giving you the occurrence. So if you can see an emission or not, calculating the growth rate is possible, of course, but it's much more complicated, and it needs much more power to calculate that. And so we do not implemented that in the code. So we have some part of the code that are doing that, but it's not in the corpus of in the body of the express code, because simulation with growth rate calculation will take a few, I don't know exactly how much time, but if you want to produce a database of that, it will require too much time. So we can do that only on a few cases, but yeah, it's possible.
Another question is about polarization. Is that true that because in the theory of CMI, the polarization, it is highly polarized. The emitted wave is highly polarized. I don't know, in the observation, is that true? The observed is always highly polarized.
Yeah, it's always highly polarized. Yeah.
It is always highly. So
for the CMI emission,
so in that way, I assume that the propagation effect is very low. So if propagation effect exists, it will sabotage the polarization. In simulation of propagation, it shows that.
We actually, here we do not simulate the propagation. Once the waves is emitted from the sources, it's propagates straight line. So
but so the it is highly polarized. So I assume that assumption is not bad. It's really satisfied the polarization. Yeah. Also in the eclipse in page 55. I noticed that if you see very closely, there is some sort of emission in between the
good spot.
Yeah. Oh, does I have an idea. Can that be diffraction of something like Poisson spots or some other resources?
Yeah, actually, we think so. We have no definitive answer on that, but we think that this could be due to some reference. So if you have your wave arriving to for example, to Ganymede or Europa or Callisto, if there is an ionosphere, the waves can be either blocked by the fully occulted, depending on the frequency of the emission and the frequency of the plasma frequency of the ionosphere, so of the density of the ionosphere. It can either be blocked, refract on this direction, or also refracting on this direction. So it's possible that in this case of Callisto, I'm not sure, because I'm not sure that Callisto has such an ionosphere, but it could be due to a reflection inside the ionosphere, the waves propagated inside the ionosphere, and so visible when you are on the behind Callisto.
Yeah. It's if it's
Just
due
my
to the
hypothesis.
refraction or diffraction, it could be calculated theoretically, but and that will be a really interesting thing if we can predict this small fraction of emissions. That would be really nice.
Yeah, actually, this is the subject of a thesis that I don't remember her name, but a colleague will begin in next September. The idea is to be able to take our simulation and take some, for Ganymede especially, take the Ganymede models of atmosphere and magnetosphere and trying to reproduce using both express and propagation tool to reproduce what we are seeing exactly here. Yeah, so good point.
Yeah, thank you. Really interesting talk.
Thanks for your question.
Great. Thanks so much again, Corentin. And I'm sure if there are more questions, they can go in the chat, or if you're happy to take emails from people.
I'm on Slack and you can send me email, no problem, sure.
Great. Thank you again so much. That was fantastic.
You're welcome.